Every time you flip a light switch, you're depending on one of the largest machines ever built. A machine so complex that a single mistake can shut down entire cities. Yet it delivers power with near-perfect reliability, every second of every day. So why do power grids almost never fail? And why, when they do, does everything fall apart at once? To most people, the power grid feels simple. Electricity comes from a plant, it travels through wires, it shows up in your home. But in reality, the grid is a balancing act happening in real time. Electricity can't be stored easily at scale. That means generation and consumption must match instantly, down to fractions of a second. If demand rises and supply doesn't follow, frequency drops. If supply exceeds demand, frequency rises. Either one can destroy equipment. The grid survives only because it's constantly correcting itself. Power grids are designed with one principle above all else: redundancy. Almost everything critical has a backup, and that backup has a backup. Transmission lines are looped, not straight. Substations can reroute power automatically. Generators synchronize to the grid so they can drop in or out without disruption. This is known as N1 reliability. It means the grid must survive the failure of any single major component, a line, a transformer, even a power plant, without customers ever noticing. Protection systems constantly monitor voltage, current, and frequency. When something goes wrong, breakers trip in milliseconds to isolate the problem. Most failures don't spread. They're contained, corrected, and forgotten. That's why the lights usually stay on. So, what actually causes major blackouts? Not one failure. Many failures happening faster than humans can react. This is called a cascading failure. Here's how it starts. One transmission line trips offline. Its load instantly shifts to nearby lines. Those lines overload and trip too. Suddenly, power plants detect instability and shut down to protect themselves. Entire regions fall out of synchronization. Within seconds, the grid fragments into islands, or collapses completely. At that point, it's not a power outage, it's a system-wide shutdown. Restarting the grid is far harder than shutting it down. This process is called black start. Power plants can't just turn on without electricity. They need power for pumps, controls, and cooling systems. Only a small number of facilities, like hydro plants or special generators, can start from zero. These plants slowly energize sections of the grid. Other generators synchronize to them one by one. It's a careful, manual process that can take hours or even days. One wrong step can force everything back offline. Today's grids face new challenges. Renewable energy adds variability. Extreme weather stresses infrastructure beyond design limits. Cybersecurity has become a real concern, but grids are also getting smarter. Advanced sensors, automation, and real-time analytics allow operators to see problems forming before they cascade. Despite growing complexity, reliability remains extremely high, because failure is not an option. The power grid is always operating on the edge of instability, yet it almost never fails. Not because it's fragile, but because it's engineered to expect failure. And when that engineering is overwhelmed, the result isn't darkness in one room, it's darkness everywhere. Thanks for watching. If you found this video helpful, don't forget to hit that like button and subscribe for more deep dives into the systems that keep our world running. Drop your thoughts or questions in the comments. I'd love to hear what you want me to cover next. Until then, stay curious, stay sharp, and I'll see you in the next video.